Hello, this is my Physics 2212 Lab 3 circuits. The purpose of this experiment is to observe the interactions between resistors, capacitors, and batteries within a circuit using the laws of conservation of energy and current, along with measuring the electric current and potential difference using multimeters and voltmeters, along with some results from our experimental process. Some fundamentals include the loop rule, the algebraic sum of all voltage drops in sources around any closed loop in a circuit equaling zero, and node rule, where the total current entering a node in a circuit must be equivalent to the total current leaving it. Additionally, we have Ohm's law that defines the connection between voltage, current, and resistance, with current being directly proportional to voltage and inversely proportional to resistance. Calculations in circuits vary depending on if the circuits are in series or parallel. Finally, we have capacitance, the ability of a capacitor to store electrical charge. A capacitor being two conductive plates separated by an insulator, where a voltage source will push electrons onto one plate, making it negative, and removing from the other, making it positive. Calculations in circuits will also vary depending on if they're parallel or in series. In our experiment 1 setup, our system is our constructed circuit and our surroundings are the environment outside of the circuit. Initial conditions include two 1.5 volt batteries, two resistors of 47 ohms and 100 ohms respectively, and ammeters. Here we can see the predicted voltage of 3 volts due to Kirchhoff's voltage law and 0.2 amps since currents 1 and 2 are equivalent to one another. For our procedure, we measured the current of the system when circuit setup was completed, which was 0.02 amps. Experimental value was equivalent to predicted current value solved for through Ohm's law. Additionally, we have some measured potential differences across the 47 ohm resistor, the 100 ohm resistor, the wires, and the ammeter, which can be seen here in this graph. We then measured additional potential difference values along the constructed circuit and calculated resistance values for the following circuit elements: 47 ohm resistor, the 100 ohm resistor, the wires, and the ammeters. Wire and ammeter resistance values needed to be zero in order to not impact the resistance of the circuit, only conducting and providing accurate ammeter readings. Here is our experiment 2 setup, where the system is again the constructed RC circuit, the surroundings are the environment outside the circuit, and our initial conditions are two 1.5 volt batteries, one F capacitor, and two light bulbs of 2.5 ohm and 5.3 ohm respectively. For the procedure, we observe the behavior of capacitor charging and discharging via connecting a light bulb, and measure the amount of time taken between charging phases. We began the charging process by connecting the battery to one of the bulbs and a capacitor in series. Visually, the light illuminated and then began to extinguish once charging is completed. The battery is then disconnected from the circuit and the bulb lights up before dimming, or rather discharging once again, along with the amount of time taken to charge and discharge for each of the bulbs. Here we can see that the charging and discharging of a capacitor follows an exponential behavior, with the discharge process taking longer because it typically occurs through a resistor, which reduces the current flow compared to a direct connection to a source of power used for charging. When using a higher resistance bulb, the charging time significantly increases, which could be seen graphically using the above voltage difference formula rearranged to compute the time constant RC. Some key assumptions were that the electron current existed at steady state, and to allow Ohm's law and Kirchhoff's current law to apply, equilibrium of charge distribution with no acting external forces was established. Here are some possible sources of error in the experimental process. For our discussion, what if you charged a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? In our ideal model, the capacitor would reach full charge instantaneously, since according to loop rule, the sum of all voltages around any loop in a circuit equals zero. Also, to satisfy Ohm's law, when resistance is zero, the current must be infinite, instantly charging the capacitor until its potential difference is equivalent to that of the battery. In real life, the capacitor would not charge instantly because there exists no material that has exactly zero resistance. Even the wire in this circuit has a very low resistance value, but not exactly zero. which is why the capacitor will charge rapidly but not instantaneously. Thank you.